Now I want to talk real briefly about what kinds of functions have inverse functions. And we say that functions have inverses only if they pass a horizontal line test. Everybody viewing this video is certainly familiar with the vertical line test. The horizontal line test is the same type of test, just we use a horizontal line and not a vertical line. Okay. Well, let's look at a function that is very familiar to us first. If I were to take a quadratic function, okay, so we've just got y equals x squared, a basic quadratic function. If I were to throw through this quadratic function a horizontal line, notice that the horizontal line hits this graph in two places. Since it hits it in two places, it has no inverse. Or I should say, has no inverse function. You could certainly take the xy points and interchange them, flip them around, and you could get an inverse relation, but that relation wouldn't be a function. That relation wouldn't pass a vertical line test. So if you don't pass a horizontal line test, the implication of that is that your inverse will not pass a vertical line test. Okay, so this particular function wouldn't have an inverse function. On the other hand, if I were to give you a function like this, now let's just say I give you some sort of cubic looking function. Okay, well, anywhere I put a horizontal line on this graph, it only intersects it at one point. This graph has an inverse function. Okay. It's just kind of a nice visual test to know if you're looking at something that would have an inverse or something that doesn't have an inverse. Well, the next obvious question you may have is, yes, we can determine if functions have inverses or not. Can we actually find them? Okay, it's quite easy to find it if you've just got a set of points, a relation, because you just flip the xy's. Well, how do we do that with an actual function? So here's how we could go about doing this. I'll list the steps first. The first step is to rewrite the f of x as y. Sometimes that's done already, sometimes it's not. In this particular example, the problem is written as f of x equals, so I'm going to rewrite it as y equals. Okay, simple step. We can all do that. Next thing I'm going to do is kind of the step that involves the definition of inverses. Is I'm going to interchange the x and the y. In other words, all of my y's are going to be written as x's and all my x's are going to be written as y's. Everything else stays the same. So this becomes x equals 2y divided by 2y minus 1. Notice the 2's stayed where they were, the minus 1 stayed where it was, just the x became y, the y became x. Okay, that's an easy step. The third step is going to be to solve for the y. Okay, this step is the one that takes work. Of any of the steps, this is the one that you have to do really kind of some algebra. So if I'm going to solve this for y, what I would do first is multiply 2y minus 1 to the opposite side. Just get that denominator out of there. So the result after distributing, I am going to go ahead and distribute this x. I would have 2yx minus x equals 2y. Okay. Now I'm going to get all my y's on one side, all my non-y's on the other. So this term I'm going to bring over here. This term I'm going to move this direction. Just using the arrows there, I'm going to skip writing underneath it the steps. So I'm going to have 2yx. That 2y comes over by subtracting it. Equals, and this x, which is already subtracted, comes over by adding it. Okay. Next, let's come over here to give us some room. Next thing I'm going to do is take out a common factor of y. If I take a y out, I'm left with 2x minus 2 equals x. And I can get y by itself by dividing by 2x minus 2. Okay. So that's step 3 done. You can see that step took some work. Okay. Final step of the process is just another rewrite step. It's another easy one. I'm going to rewrite the y as f inverse x. That negative 1 exponent is the notation that we commonly use or universally use to represent inverse. So I rewrite this as f inverse of x equals x divided by 2x minus 2. There's how we find our inverse function. Now, as examples go, that was a rather challenging example. That's about as hard as you're going to find anywhere in your homework, probably as far as finding an inverse. One more example of finding an inverse function algebraically. Let's run through the steps again. I'm not going to write them down this time, but if you wrote them down, you can go back and reference them. First thing I'm going to do is rewrite it as y equals. Next thing I'm going to do is switch the x and the y. And now I'm going to solve this equation for y. When I solve this equation for y, the first thing I do is I cube both sides. That gets rid of the cube root. So I've got x to the third equals y minus 2. I'm then going to take this minus 2 and move it over here. So I have x to the third. Since it's subtracted, I have to add it. Plus 2 equals y. So there you can see it was rather simple to solve for the y, just a couple of steps. The last step is to use a notation change. The y is the same as f inverse of x, and it equals x to the third plus 2. Last thing I want to talk about in this section is called the inverse composition rule. It states that two functions, let's name them f of x and g of x, are inverses if f of g of x equals x and g of f of x equals x. So in other words, if we check the composition and when we compose the functions, the result is simply x, and those functions are what we call one-to-one functions, and they are inverses of each other. So let's do that on the next slide, show one example of that. Directions say verify the two functions are inverses. So I'm going to check the inverse composition rule. I'm going to check f of g of x, which says take the g function right here, put it into the x in the f function. Okay, so the f function is a fraction. I have x plus 3. The x is going to be 4x minus 3. Here's my plus 3 divided by 4. And we're just going to simplify this. The minus 3 plus 3 cancels, so I get 4x divided by 4. The 4's cancel, so I get x. So that checks out when I compose them that way. Now I'm going to compose them the other way and see if it works that way too. So now I'm going to check g of f of x. So I'm just going to reverse the composition. I'm going to put this function into this one's x. So I have 4 times the quantity x plus 3 divided by 4 minus 3. If I work this out, this 4 and this 4 cancel, so we have x plus 3 minus 3. 3's of course cancel, we have just x, so that checks out too. So are these two functions inverses? Have we verified that these are inverses? Yes, these are inverses.